Okay, so I want to talk about how we would know whether a system is Hamiltonian or not. So let's suppose that I have an autonomous system like this, where x prime is f of xy and y prime is g of xy. I am going to require that f and g be continuously differentiable. Your textbook omits that condition, and they really shouldn't. Okay, so our question is the system Hamiltonian? And what I'm going to do, first of all, is I'm going to say, well, what if it is? What would be true? And then I'm going to hope that what I get is actually a criterion, that if that criterion is true, then I will know that it's Hamiltonian. So if so, if it's Hamiltonian, then I know that f is actually the partial of h with respect to y. And g is equal to the opposite of the partial of h with respect to x. It is very important to remember that that's what would be true if the system is Hamiltonian. Because remember, what we were looking at is saying that basically dh by dt, which would be partial of h with respect to x, times dx by dt, plus partial of h with respect to y times dy by dt, we're trying to make that equal to 0. Okay. So if f is giving me dx by dt, or x prime, I'm going to be multiplying that by the partial of h with respect to x. Okay. I don't want this to be the partial of h with respect to x, because then I'd just be squaring that. And then if this was the partial of h with respect to y, I'd be squaring that. The only way I'd get 0 is if everything was 0. Okay. What I want is that since what I'm multiplying this by the partial of h with respect to x, I want it to be this factor here. And I want this to be the opposite of that factor there, so that in each term that I get from the chain rule, I get one factor of the partial of h with respect to x and one with respect to y. Okay. All right, so if it is Hamiltonian, I have this. Looking for my eraser. Okay. All right, now I can use the fact then that this is already a first partial of h with respect to y. If I were to take the partial of f with respect to x, that would be the partial with respect to x of the partial of h with respect to y. That's del squared h by del x del y. That's one of the two mixed second partials of h. If I wanted to get a mixed second partial here, I'd take the partial of g with respect to y. That would be the partial with respect to y of the opposite of the partial of h with respect to x. That's going to give me the opposite of the second partial of h, taking the partials with respect to x first and then y. So this gives me the opposite of the other mixed partial. But I know if f and g were continuously differentiable, that's telling me that these functions here are continuous. If they're continuous, the mixed partials would be equal. Okay. So if the mixed partials are equal, that means that the partial of f with respect to x would be the opposite of the partial of g with respect to y. Okay. That will always be true if I have a Hamiltonian system. It turns out that if that is true, I have a Hamiltonian system. Okay. So a system will be Hamiltonian if the partial of f with respect to x is the opposite of the partial of g with respect to y, where f is the function that's giving me my x prime or my dx by dt, and g is the function that's giving me my y prime or my dy by dt. Okay. So that's how we'll be able to check for whether a system is Hamiltonian or not. So let's just take a look at an example of a system. Okay. let's suppose I have x prime is equal to x times cosine of xy. Oops, that's x prime. And y prime is negative y times cosine of xy. This is actually the system from problem number 2 in your textbook. It's an even numbered problem that I did not assign. Okay. So I want to check to see, is this system Hamiltonian? So I'm going to just name this F and this G. Okay. And now I'm going to take the partial of F with respect to x and the partial of G with respect to y. Okay. So the partial of F with respect to x is partial with respect to x of x cosine of xy. That's going to be a product rule. So the derivative of x would just be 1 times cosine of xy plus x times the derivative here is going to give me a negative sine of xy times the partial with respect to x of x times y would just be y. So that's going to be cosine of xy minus xy sine of xy. Okay, let's take the partial of g with respect to y. That's the partial with respect to y of negative y cosine xy. So that's again going to be a product rule. The partial with respect to y of negative y is just negative 1 times a cosine of xy plus a negative y times the partial here will be a negative sine xy times the partial with respect to y of xy is going to be an x. Okay. So I've got negative cosine of xy. These two negatives will combine to make it a plus, and then I'm just going to put that x up at the front, so plus xy times sine of xy. Now, these two things are not the same. I don't want them to be the same. I want them to be exact opposites of each other. And they are. Because here I have a positive cosine of xy, here I have a negative cosine of xy. Here I have a negative xy sine xy, here I have a positive xy sine xy. So I do have that the partial of f with respect to x is the opposite of the partial of g with respect to y. So I know that my system is Hamiltonian. Now, what that means is that I know that the solutions are going to be level curves for my Hamiltonian function if I can go ahead and find a Hamiltonian function. So that's what we're going to do in the next video. Before I do that though, let me just comment on something that we did earlier in the semester where we were also looking for level curves of some function, and it's really easy to confuse the two. Okay, so we looked at exact differential equations earlier. That had the form of m of xy dx plus n of xy dy equaling 0. Okay. So this was a differential equation that involved just differentials rather than full-on functions that were the derivatives. We said this would represent the total differential of some potential function, which we generally called f, if this was the partial of f with respect to x, and this was the partial of f with respect to y. If that's the case, then this is exact. And so we were saying this is already a partial with respect to x, so the test for whether it was exact was if when I took the partial of m with respect to y, which would give me a second mixed partial of f, I got the same thing as the partial of n with respect to x. So there, for checking for exactness, we were using the equality of mixed partials, but we had to remember that if it was exact, this was already the partial with respect to x. When we're looking at Hamiltonian systems, There's a lot that's similar, but there's a lot that's different. We're looking at dx by dt equaling f of xy. If it's Hamiltonian, that's the partial of h with respect to y, not with respect to x. And if we look at dy by dt, which we're calling g of xy, if it's Hamiltonian, that is the opposite of the partial of h with respect to x. So two important changes. One of them is a perfect match, one of them is the opposite of that. The other is that the one that we're associating with x is actually the partial with respect to y. Whereas over here, the function that's getting multiplied by dx is, if it's exact, the partial with respect to x. Okay. So here, the test for whether it's Hamiltonian or not is whether the partial of f with respect to x, the function that I associate with x, I take the partial with respect to x, is the opposite of the partial of g with respect to y. Okay. So, a lot of similarities, but a lot of really, really important differences. Rather than just trying to memorize, okay, if it's going to be exact, I have to check this and this. If it's going to be Hamiltonian, I have to check that and that. Try to understand the concepts behind it. That the idea here is that if this is exact, this represents the total differential of f, which is the partial of f with respect to x times a variable that represents a small change in x, plus the partial of f with respect to y times a variable that represents a small change in y. On the other hand, here, where we got this was that when we applied chain rule, we had a sum of two products that we wanted to equal 0. And so we said we were going to rig it so that these things, which showed up as factors in those products, made it so that those two products were opposites of each other. Since we're trying to get them to be opposites of each other, it makes sense that one of these is positive and one of these is negative. So spend some time trying to just look through again the rationale behind why this is what we're testing. Hopefully that will make it a little bit easier to remember what it is that you're testing. And am I supposed to be taking the partial with respect to x or with respect to y? And is it supposed to be positive or is it supposed to be negative? Okay, when we come back in the next video, since we have demonstrated that this particular system that we had was Hamiltonian, we will try to find our Hamiltonian function h of xy.